Okay, welcome to the RL Theory seminars, everyone. Today we have Andrew presenting for us. And just like as a reminder for how these seminars work for everyone, so the presentation will be 50 minutes, that's 50 minutes. And during the presentation, feel free to just unmute and ask any questions to Andrew. And if you'd like, you can also ask your questions in the chat, and then I'll unmute and ask Andrew. If you have longer questions, we'll have like a Q&A session after the talk, about like 30 minutes long, or maybe a bit shorter. So you can ask your longer questions then. Other than that, we'll have Chaba here co-hosting. He'll be asking Andrew some technical questions if there isn't others. And other than that, we have just like a brief bio about who Andrew is. Andrew's a final year PhD student at the Computer Science Department at the University of Washington, working with Kevin Jameson. And he's, in particular, much of his work is focused on obtaining better than worst case guarantees for reinforcement learning and learning in dynamical systems and algorithms, which provably adapt to difficulty and perform optimally on each particular problem instance. And today he'll be talking about reinforcement learning as well. So you can get started now.
Great. Well, yeah, thanks for the introduction and invitation to present. So today I'll be talking about some work I did sort of about using offline data, combining it with sort of online RL techniques. And this is joint work with Aldo Paciano, who at the time was at MSR, now is primarily at the Broad Institute at MIT and Harvard. Okay, so just to jump in, so we're probably sort of all aware of, various sort of now, we may say now sort of canonical examples of RL succeeding in different settings, things like AlphaGo, or this is sort of OpenAI's Dota 2. And what these sort of, a lot of these examples have in common is that they really required a huge amount of interactions of samples to get sort of good performance. So for example, in the instance of Go, you had roughly 10 to the 8 games that were played. For Dota 2, you had roughly 10 to the 5th, like 10,000 years of gameplay. So these are like really large sample complexities and impractical for most problems. And kind of the key thing in both of these examples was that the samples were all collected online. So these were sort of all online interactions with some sort of game system that the agent required in order to sort of like learn how to perform effectively. Now, at the same time, we've seen both in RL as well as ML more broadly, a lot of successes in recent years of using sort of log data or offline data. So, just one example that is sort of very prescient is systems like ChatGPT and LLMs. These are trained primarily on just like massive corpuses of text to do a very simple task, that next word prediction. And using sort of all this offline data, you can actually build like pretty powerful interactive systems. And so, we sort of see both of these systems require huge amounts of data to get good performance. But on one hand, we have these sort of online RL systems, which require sort of online interaction. On the other hand, we have systems that are just learning from large amount of log data. And if we have log data, this is potentially much cheaper, much easier sort of, rather than going out into the world and collecting data. And so what a lot of sort of, the RL community broadly over the last few years has focused on developing techniques for learning from log data. And this is sort of this whole offline RL literature of which now, we have a pretty good understanding both in theory and practice. And it has had a lot of successes in learning from this log data. But sort of this offline RL literature is not has some maybe like limiting factors to it. And one of it is we just think about how does the complexity of offline RL typically scale? And how it typically scales is with this term that we'll just call like C star, which is essentially the offline data's coverage of the optimal policy. And there's a lot of variations on how do you actually form it, or like what is the precise definition of C star, whatnot. But like sort of morally, this is what a lot of these papers are saying, and also this is kind of known to be tight. That to do offline RL, we usually need sort of coverage. We usually need the offline data to cover the behavior of the optimal policy or an optimal policy. And if that condition is met, we can usually use these sort of pessimistic techniques, and we can get good performance. And so this is great. When our offline data is rich enough that it covers the optimal policy, but this is not necessarily always the case, right? We might have scenarios where we have a large amount of log data, And maybe this data contains some amount of useful information, but it just doesn't actually cover perhaps the optimal policy, or it only covers part of the optimal policy. And in these settings, like sort of the offline RL results we have would essentially tell us that offline RL is not able to give us an effective policy. And furthermore, this is kind of actually known to be tight. And so we sort of have in two hands. We can sort of look at these two settings. In online RL, the learner can interact with the environment as many times as they need it. They can sort of go out and collect the data they need to solve the problem. In offline RL, at least a typical setting, the learner just has access to a log data set and they can't interact. They can't go out and interact with the environment. And so, the advantages of online RL is that we can get these, we can learn these very powerful systems, say systems that are good at really complex video games like Dota 2. The disadvantage is that, to do this, we really require a huge amount of online interactions. And offline RL, on the other hand, we can make use of large amounts of offline data, of existing data. We don't actually have to go out and collect online data, which could be really expensive. But at the same time, we're limited in the effectiveness of the policy we can learn by these sort of C-star, these coverage factors. And so what we're kind of interested in looking at in this work is really, can we kind of get the best of both worlds? Say we have some offline data. Perhaps this data is not good enough to sort of actually learn the optimal policy. Maybe that coverage doesn't completely cover the optimal policy. But maybe it gives us some information about the problem. Can we sort of use this data to actually then perhaps combine this with online RL to minimize the amount of online samples we need, but sort of allowing us to still solve the problem by collecting enough online samples to learn the optimal policy. So that's kind of sort of the goal of what we want to think about here, sort of combining these offline data sets with some amount of online interaction to allow us to actually learn a good policy. Okay, so just as an example, let's think about sort of a simple sort of weather balloon example. And this is actually, I chose this because this was another instance of DeepMind had a paper on using RL for weather balloons. So this is a setting where RL has actually been used. But let's say we sort of have a weather balloon and we want to think about having it fly in, say, several different conditions. So maybe sun, wind, clouds, and snow. And in particular, we'll just sort of restrict our goal to sort of just a subset of these conditions. Maybe we know it's never going to be going in cold temperatures, so we can sort of just, we just want it to perform well in sun, wind, and clouds. And let's also assume that we have some amount of offline data that covers part of these scenarios, but not all of them. So maybe we have offline data in both sunny conditions and windy conditions, but we don't have it in cloudy conditions. Okay, so our goal here is to learn a good policy in sun, wind, and clouds. We only have data in sun and wind, so how do we approach this problem? Well, the first thing we could do is we could just train a policy in the offline data and hope it generalizes. Again, this is sort of actually known to not work because C-star in this case would be small, or would be large. We don't have coverage of the optimal policy. This is a bad idea. If we just went for the fully online case, we could just collect sort of online data and we could cover all of the space. And this would sort of be what sort of standard online RL algorithms do. And this is not really great either, obviously, because we already have data coverage in half the space. And so what we're gonna do here is we're gonna really think about the focus of this work is really thinking about how do we actually precisely augment the coverage of the offline data. So the picture looks something like this, where we have offline data coverage covering sort of some of the conditions already, and we just target our online exploration on sort of the regions of interest, in this case the clouds, that do not have data coverage. And so really the two fundamental questions are, well, how do we how can we actually improve this data coverage? How do we actually sort of go out and collect data that covers only the relevant regions not covered by the offline data? And then sort of given this, how do we actually even best combine the offline and online data in some way so as to then learn a good policy? And as I was saying, sort of the majority of the RL literature considers either the pure offline setting where there's sort of no online interaction, or pure online setting where there's no offline data, although there have been other papers, and I know actually Ayush last week presented another work sort of on a similar setting to this. So there is other work on this problem, although when we published this paper, there was not very much out there yet. So we basically, well, I won't go through all the contributions here, but we basically sort of develop an exploration approach that is able to do this. Okay. Any questions on the problem setting before I dive into more technical?
I think it's all clear.
Cool. Okay, so we're going to be looking in this work sort of at episodic RL. So we have some agent, we have an environment, sort of standard episodic RL setting. The agent, a state is sampled from the environment. The agent takes an action. They receive a new state and a reward, and this proceeds for big H steps, at which point the process repeats. And we, of course, assume that both the transitions and the rewards are initially unknown. And we're going to be looking at a setting of linear MDPs, where sort of we have some known featurization of our environment, phi of SA, which maps to some d-dimensional space, and the sort of transitions as well as rewards are linear in this featurization, phi of SA. And so, obviously linear MDPs are, not perhaps the most expressive setting, but actually sort of, as we'll see, give us enough, it's sort of non-trivial enough in this setting that I think is still an interesting thing to think about in terms of understanding coverage in RL. So we'll be focusing on the linear MDP setting. Just a few notational things. We'll define the value of a policy as V naught pi. This is simply the expected reward for policy pi. V naught star denotes the value of the optimal policy. And we'll make the assumption here that we have access to some offline data set, call it D, that has T off trajectories in it. And we just sort of assume that this data set was collected on our MDP that we care about. We're not going to make any other assumptions on it. It could be sort of collected by a good policy, a bad policy, whatever. Actually, in fact, the results in the paper doesn't even have to be full trajectories. It can just be sort of like arbitrary samples, as long as they're sort of generated on our true MDP. Okay, and so then the goal of this paper is really, again, given this offline data set, identify some policy pi hat, such that with probability 1 minus delta, this policy has a value within fraction epsilon of the, or value epsilon of the optimal policy, and do this using as few online interactions as possible. So we assume that the offline data is effectively free, like that we sort of just have this offline data, wherever that we got this, is sort of not the question we're interested in here. And we can use these samples in any way we want, and sort of there's no, it doesn't sort of cost us anything to use these samples. And so what we're really interested here is minimizing the amount simply of the online samples. We want to sort of collect as few online samples as possible in order to sort of find an epsilon optimal policy. Okay, so how do we think about doing this?
Maybe you should just ask the question, Chaba, because I think Andrew can't see us.
Oh yeah, I can't see the chat,
Oh,
sorry.
okay. Yeah, I was just raising my hand. I guess like maybe I'm just jumping forward, but one would think that like what distinguishes the offline data that was collected by some arbitrary means from what you would do if that the same data or like data was collected through your online algorithm. Like, so the online algorithms usually just, given some data, they're building some model or doing their things, calculations, and then they go on deciding about what actions to take and so on and so forth. And so the immediate thought is that can we just like empirical mindset, just run these algorithms and like don't care about what's the origin of the data?
Mm-hmm. Yeah, so that's like more or less what we will be doing.
Okay.
So I think there's questions though even there as to like sort of how to best do this, right? So we could just sort of, take any online RL algorithm, put in the offline RL data, say we're running a UCB style algorithm, we sort of just like warm start our confidence intervals with the offline data and just keep running it. This is totally something you could do. But it's sort of a question still of like, is that the best thing you could do? Or like, how do we actually, like, it's not entirely clear if you do that, like, if you're going to actually like sort of be exploring then in the regions that are sort of most necessary to fill in the missing bits or whatever. And so that's kind of what we'll see, how to actually think about doing that here. But sort of like what we're doing is really more or less sort of what you described, which is we sort of are using it as online as in the same way we would use online samples.
Okay. All right. Okay.
Yeah.
I wait patiently.
Okay. Any other questions?
Good. I think.
Cool. Okay. Okay. So what we'll define here is, so given this offline data, we'll define the offline covariance as lambda off H. So these are sort of the covariance of the offline data at step H. And it's sort of known that like, I won't go through the details of this, but in linear MDPs, just like linear bandits and other sort of linear regression settings, the uncertainty in some direction phi, given some data lambda off, is going to scale as phi in the sort of lambda h, lambda off inverse norm. I don't know if I put the definition of this, but this is simply the square root of phi transpose lambda off inverse phi. So this sort of gives us a quantification of uncertainty in the offline data. We'll also define here the direction of the policy pi, phi pi of h. This is the expected feature vector that policy pi will encounter during operation. Okay, so you can think about phi pi of h as sort of like quantifying something like where policy pi is reaching, at least in some expected sense. So if we think about sort of an example like this, the sort of the arrows I have here are sort of corresponding to maybe something like phi pi of h, right? That each of these settings is kind of pointing in some different direction. There's sort of a different feature in each of these settings, and so what we'll see is that sort of what we want to do is to learn about each of these directions. We sort of need to cover the directions of the corresponding phi vectors. Okay, now we'll also define sort of the offline data coverage for policy pi. It's given by c pi of d. This is simply essentially this concentrability where we just look at basically for policy pi how much coverage we have in direction phi pi of h. And it's known, again, sort of going back to these like existing works in offline RL, that if you just have the offline data, you can obtain some policy pi hat from the offline data with some optimality that's bounded as c pi of star times c pi of star for your data set T. I'm sorry. Okay, so in this scenario, we see that sort of the suboptimality of the policy, at least if we use sort of standard offline RL algorithms, is sort of controlled by how much our data, the lambda off h, the offline covariates, how much coverage it gives in the direction of pi star and sort of phi pi star of h. And so sort of naturally we might think that, well, if we have some offline data and we want to sort of improve the performance of our algorithm, what should we do? Well, we should simply try to augment the offline data with some amount of additional online data that ensures that in the direction phi pi star of h, we sort of have like good coverage. Basically, we want to explore in direction phi pi star of h. Okay, this is sort of like a very reasonable thing you could imagine doing. It will sort of make the c pi of d smaller. That will then translate to smaller suboptimality. And so indeed, this is actually what we will do. So our hope is going to now be to augment the offline covariates, lambda off h, with some online covariates that sort of just, ensure that we get good coverage in phi pi star of h. And this, this is like not anything, I'm not really saying anything super profound here. This is kind of, you would see that this is the reasonable thing to do just from, existing work on offline RL and whatnot. The question though is how do you actually like do this and how do you do this efficiently? If we want to achieve this, this is maybe sufficient, but we don't actually know pi star, and so we also don't know phi pi star of h. Essentially, we don't know what direction we should be exploring in. So we want to collect online data that sort of gives us coverage in the direction pi star, but we don't sort of like, A, we don't know what direction that is, and B, we don't actually even know how to go out and collect data in that direction. And so, while this is maybe sort of a reasonable objective, it's kind of like unclear how you actually like go and satisfy this. And we kind of, I think offline RL literature kind of like gets around this because it never actually goes out and collects anything. It just sort of like looks at the data it has and says, well, look, the complexity scales sort of with the coverage of this data, that's that. But if we want to actually augment this coverage, we need to sort of think about how do we actually go and sort of target our exploration to do that. Okay, and so we basically, we're going to propose the following algorithm, which we call fine-tune pedal. So this is actually based on an algorithm that I came up with prior to this paper, which is published in another paper of mine that was called pedal. So this is sort of a extension of pedal in some sense to the case where you have offline data. And this algorithm is essentially a policy elimination algorithm. And so what we do is the following. We take as input, again, some tolerance epsilon and some confidence delta, as well as the offline data set D. And we're gonna maintain some set of policies, y1, which we can sort of think about as an initial set of covering policies. So this is essentially the set of all possible policies. So there's sort of nothing, you don't need prior knowledge to construct this set. You can construct a set of such policies that that we sort of just want to ensure contains an epsilon optimal policy for our MDP, and you can do this. Okay, so you construct this initial set of policies, and then you proceed in rounds. So at round L, we're going to define our tolerance, epsilon L, to be 2 to the negative L. So at every round L, it's getting sort of cut in half. And then at round L, what we're going to do is we're going to try to collect data that satisfies the following. So we're going to collect covariates lambda HL, such that for all policies pi L in our active set, in the sort of estimated direction they are pointing, which we denote here by phi pi hat of L, we sort of have good coverage. And what that coverage means is that sort of this confidence interval essentially is less than epsilon L squared. Now, once we've sort of collected this data, and I'll spend some time later on in the talk saying how we actually collect this data, but we have a sort of an efficient way to sort of collect data that achieves this. For every pi in the active set, we're going to estimate the direction it points in, this phi hat pi L, using the offline and online data. And we do this for each h, and then at the end, we sort of just eliminate policies that we can show are suboptimal. So we sort of use the data to estimate the value of the policy. What we can show is that sort of our estimates of the value of the policy are good up to a factor of epsilon L. And so we eliminate all policies that are more than 2L, epsilon L suboptimal. So for those of you who are familiar with action elimination style algorithms from the Bandits literature, this is essentially like a generalization of that to RL, where we're doing like policy elimination over the space of policies. Now, I guess I will just remark before somebody asks, this is not in general computationally efficient because the set pi, in general, you need to be exponentially large in the dimension to ensure that you have an epsilon optimal policy. So we sort of have to like enumerate an exponentially large set to run this algorithm. So you can't really do this. So this is really more of a statistical result. It may be possible to make computationally efficient. We just didn't really think deeply about that. Okay, so this is kind of the idea though, which is that we're going to, we don't know what the direction we should collect data in. So what we do is we sort of like gradually narrow down the set of policies that might be a good policy. And we try to just focus our exploration on the sort of remaining set. So at round L, the policy pi L will only contain epsilon L suboptimal policies. And so we sort of try to focus our exploration then on just those policies, gradually sort of refining our estimate of the value of these policies by shrinking epsilon L here. And so what we can show with the we can essentially show the following.
I have a quick question before you move on. Like, back to this policy covering thing, like, how are you representing this initial set of covering policies, or like, what did you mean by you can get this?
Yeah, so you can show that like basically, basically you can represent the optimal policy for any reward function in a linear MDP as sort of essentially linear in phi of SA. Okay, so the Q functions in linear MDPs are linear in phi of SA. And so if you sort of argmax those Q functions, you have sort of phi of SA inner product sum vector W pi.
Yeah.
If you argmax of that for any given state, that is an optimal policy if this W pi vector is correct. So we essentially cover the set of W pi vectors. And then what you actually need to do is you need to make this like smooth in some sense. So we sort of use a softmax policy over these sort of like, so you essentially just cover the set of possible Q functions in linear MDPs. And then you sort of set this set of policies to be like softmax policies over that set.
Mm-hmm.
And then you can show that this will contain an epsilon optimal policy for any reward function, but it is exponentially large in the dimension. So it's, not ideal computationally, but statistically it's like fine.
Okay.
Yeah.
Is the softmax really necessary?
I think it is. I mean, maybe it's possible it's not. Like I tried initially getting it without a softmax, but the issue was like when I wanted to like show this coverage. So the issue is if you don't use a softmax, then like you sort of will have like a jump where you have like one W, another W very close to it might induce actually a totally different policy. because you're taking a max.
Right,
The softmax allow you to like smooth this out and show there's some continuity, which makes the covering argument work more easily. But it might be possible to do it without. I didn't like spend that much time on it.
Okay. Yeah, it's the old familiar problem that argmax changes quickly. Yeah, like question is whether the induced distribution is also changing quickly or not.
Yeah.
Yeah. Okay.
Yeah, I definitely could use. I mean, I don't think you get a tighter result, but like, for maybe practical reasons, it might be.
Yeah.
Yeah. I guess I'll also remark here too. So the algorithm that I'm presenting here is essentially identical to this pedal algorithm, which again, is from a different paper. The only difference being that we essentially augment this here, essentially this confidence interval, with the offline data. So the pedal algorithm is essentially identical, except you have no offline data. So to Chaba's question originally, like essentially what we did is we just took an online algorithm, we augmented the confidence intervals with the offline data, and that's our algorithm. The key though, as we'll see, is really just like the exploration method we're using to ensure this is met is like very precise and allows us to actually like really explicitly explore the directions not covered by the offline data. Okay, so let me just go and state sort of the main result from this. So we define the following, which is the sort of, we call the offline to online coefficient. And this is defined to be the minimum time t, such that for the best possible exploration policy, pi exp, and for all policies, and for the worst case policy pi, this condition is met. Okay, so let me just explain this really quick. So what this says essentially in the denominator, we have the gap, the suboptimality of policy pi. So this is v naught star minus v naught pi squared. You can think of this analogously to sort of gaps and bandits and whatnot. It's just sort of the policy gap. And so what this is essentially saying is that for better policies, for policies that this gap is really small, you need to, that will make this really large, which will sort of force you to get like stronger coverage in that direction. But for policies where the gap is really, really, really large, then this denominator is really large, and so you don't need as good a coverage. The numerator then says essentially this phi pi of h in this inverse norm essentially says what is the coverage that the offline data, lambda off, plus t steps of running policy pi exp, what coverage that gives in direction pi. And so you can sort of think about this as a quantifying in some sense how easy it is to reach policy pi, or sort of how easy it is to get coverage in policy pi, or how easy sort of how easily we can get coverage in direction phi pi given our offline data. And so, if we're in a scenario where we sort of have really good coverage from the offline data on the near optimal policies, that's going to be the case when this gap is really small. And so in that case, this constraint is actually pretty weak. Like it's essentially saying like you sort of have, for these policies where the gap is small, you don't actually need to collect any online data. You can sort of just rely on your offline data. And that will sort of make then sort of the t really small. But if you're in a scenario where perhaps the offline data coverage is not good for the policies that have small gaps, that are close in value to v star, then this would essentially say, well, you actually need to cover these completely with your exploration policy pi xp, and so that will make the t much larger. So what this is really doing is sort of trading off how much coverage we want to get on every policy, which scales something like a suboptimality, with sort of the offline data we already have that is covering it, and the best case exploration policy. So I don't think I should define it here. I think I forgot to put it on the slide, but this is essentially the coverage of policy pi xp. Okay, so given this complexity, what we can show is that our algorithm collects at most essentially this T020 summed over the horizon H online episodes and returns some policy pi hat that is epsilon optimal for some value of beta. So this is beta is sort of our confidence interval width in some sense. And so again, what this really says is it sort of trades off explicitly between the coverage of the offline data, the coverage of the online data, and how suboptimal sort of the policy is and how much coverage we want to get on a given policy. And our algorithm is able to explore in kind of this like minimal amount of coverage. Okay, any questions on this result?
Maybe. So there is some maybe inefficiency in that every stage is treated as separate, although I understand this is the inhomogeneous case, but
Yeah.
yeah,
Yeah, so that is correct. We treat every stage as separate, and this, yeah, I mean, it's potentially suboptimal by a factor of h, because
yeah,
of that. Although there's other, we're already sort of not tight at h factors for other reasons.
okay,
So the h dependence is not optimal here.
I see. Yeah, it also feels difficult though to somehow connect the stages, and yeah, I don't know.
Yeah.
Although the
We thought
algorithm
about
is
this
like
for,
this is somehow explicitly baked into the algorithm now.
yeah, it's
Is it?
basically, so basically what we're doing is like you're trying to explore for a given stage. So at every step h, we try to find an exploration policy that sort of minimizes this. The reason actually that we can't do it, we can't link all the stages together, is that you use the data that you collect at stage h to estimate where policies at stage h+1 are going. And so you kind of need to, like, at least to run this algorithm, it seems you need to do sort of this in like a sequential fashion, where you estimate what's
Yeah,
going on at stage h, you use that to figure out where you should be exploring at stage h+1, and then you
yeah,
go explore to stage h+1 and you
yeah,
sort of iterate on this.
yeah.
Whether or not this is improvable, yeah, it's unclear, but it doesn't. I'm not sure how it would be for this
Okay,
style algorithm.
thanks.
I also have some questions. Oh, and I can ask the question in the chat first, actually. So someone said, "Am I reading this correctly that FT Pedal doesn't care about C star or how good the offline data is?"
So this is a good question. So we don't have any explicit like C star dependence, but it does care about how good the offline data is, from what I was sort of just saying. So again, to meet this condition, you need to have more coverage. You need to make the covariate smaller for policies that are really good. So if, say, pi is like really close to pi star, this gap will be really small. And to ensure then that this whole fraction is less than 1 over beta, that means you need a lot of coverage of the combined offline and online data in this sort of this direction. And so if our offline data actually already has like excellent coverage in this direction, then that would actually say the amount of online data we need in this direction is like very little or none. And so this is sort of like somewhat analogous to C star in that like it's sort of saying that if the offline data already has really good coverage on the optimal policy, we really need like almost no online data or very little. We might still have to explore a little bit in the sort of suboptimal policies, but it sort of scales like sort of morally similar to C star. I have in a few slides though, I will have a little bit more to say about comparing this complexity to C star exactly. So
Yeah, I
maybe
have some.
can
I have
hold off on
another.
that until then, but yeah.
I have another slight follow-up question. First of all, this. So you're saying like for all data gathering distributions, or sorry, like all like these data sets D, this calligraphic D, it's bounded by this like T020 thing is bounded by 1 over beta.
Mhm.
And like the thing you wrote there with the beta being this big O of D, is that supposed to be 1 over beta is equal to this?
No, I think this is beta because this is essentially saying that like the sort of confidence interval width, if I were to rearrange this, the confidence interval width for policy pi is beta
Oh,
times this.
I misread this thing. Yeah, so sorry.
Yeah. So you
I
want
miss
sort of beta, you want the confidence interval, which is beta times this, the
yeah, yeah.
numerator here to be less than the gap, which is what this is saying.
Yeah, I didn't see the such that part of this whole thing and was very confused. I see. Or subject to part.
Yeah.
I understand now. Okay.
Cool.
I'm good.
Other questions on the result?
I think we're good for now.
Okay. So so we have sort of a couple different like lower bound or examples that sort of like build off of this. So first we sort of just have the lower bound that says in some sense this complexity of showing this TO2O is necessary. So we can construct a class of MDPs and some offline data set D such that any algorithm must collect at least TO20D samples. Now you'll notice sort of the here I have TO20 beta for some sort of general beta. The beta here is different. Now it's just DH, so this is sort of gets at the suboptimality and H factors. But still, you sort of need to collect this many samples in order to find some policy pi hat that is epsilon optimal on some m with constant probability. Now the quantifiers here I didn't actually like precisely state, but we can sort of state this for any sort of you sort of give me any T off, any amount of offline samples, and you can construct a scenario where this is necessary, where given T off offline samples, I need to collect this many more online samples to ensure that I'm epsilon optimal. So in some sense, the complexity we have on the previous slide is like not improvable. You can construct scenarios where you actually do need this many online samples in order to solve your problem.
Yeah, about the quantifiers. So you're saying what are we fixing here?
So you fix I will construct a family of MDPs, and given a T off, then I'll construct an offline data set on those family of MDPs. And then for that family of MDPs and that offline data set with T off samples, you need to collect this many online samples. There is also actually another quantifier though, which is that I didn't just collect a totally like bad offline data set. So the offline data set has like full rank covariance. So it's sort of a good offline data set of arbitrary size. You need this many online samples.
See. Okay, so it's the number of samples in the offline data set that is fixed. I guess the features are fixed.
The features are fixed.
And and then you construct everything else. Yeah, and the features have to be such that like some full covariance thing must work, because otherwise, yeah, of course, this won't be true. Okay. Rich enough features.
Yes, so it's not like just totally like you could imagine a scenario where like I construct an offline data set that's like really bad and then it just does nothing to help my problem. Sort of in this scenario, yeah, I should have put all the quantifiers in this theorem statement. But in this scenario, the offline data set is not like really bad. It's actually giving you some useful information, but still with that useful information, you need to collect this many more online episodes.
Right.
Okay. So another question that we can ask from this is like, can offline data provably help in some way? Right? Are there scenarios where this complexity I've shown you with the offline data is better than what you'd get for either sort of just online RL or just offline RL? And so we have a scenario where this is the case. So we have an example where there's two MDPs, M1 and M2, and some offline data set D. And this data set D is actually sort of could have been generated on either M1 or M2. So M1 and M2 only differ on certain states, and this data set doesn't actually include coverage for those states at all. And so we can show that using sort of this data set, if our goal is to learn an epsilon optimal policy, any algorithm which returns some pi hat using only the offline data must have some optimality that is at least square root of epsilon. Right, so if our goal is epsilon optimal, the square root of epsilon could be substantially larger, so we can't sort of meet our goal of getting an epsilon optimal policy. Any algorithm that does not use this data set must collect at least 1 over epsilon squared online episodes to identify an epsilon optimal policy. But any algorithm, or our algorithm, is basically able to find an epsilon optimal policy with complexity that scales as 1 over epsilon to the 8/5 online episodes. And so basically this yields an improvement in a factor of 1 over epsilon to the 2/5 over the purely online samples, while achieving this goal of learning an epsilon optimal policy, which the purely offline samples are not able to do. So this epsilon to the 8/5 is kind of weird. I admit it's sort of due to the some of the lower order terms in the complexity, which I didn't really highlight. You sort of pick up some, like in this example, some like larger factor here. But I think it's instructive to think about the example just to give an idea of what is going on here. So what we have is we just have actually a really simple 3-state MDP where you have some state S1 you start in, and then you transition to either state S2 or S3. And you assume sort of that the offline data covers all the actions in S1, all the actions in S2, but only one of the actions in S3. So you have no offline data from action A2 or A3 in state S3. And furthermore, you'll transition to state S3 with probability at least square root epsilon. And so where the suboptimality comes in from using only the offline data is that what we can show is that because you don't know, you don't have any data from A2 or A3, you can't identify which of these actions are optimal without further exploration. And so so you can show in this example that you will choose with constant probability, or on one of these examples, you will choose the wrong action, and then you'll pick up a total suboptimality of square root epsilon. So this is why the sort of purely offline method doesn't work, because it doesn't have good coverage on A2 or A3. Because that's what you said. But we can also show then that we can also construct it in a way such that S2, to solve for the optimal action in state S2, would in general take 1 over epsilon squared samples if you have no prior knowledge. And so using the offline data, we assume we have good enough coverage that we sort of already have 1 over epsilon squared samples for S2, for all the actions in S2. And so we can actually identify what this optimal action is in S2 without any additional exploration. But if we ignored that data, we would need to pay a 1 over epsilon squared samples. And so our algorithm is able to sort of combining this offline and online data. You can see that what you really should do is you should be directing your exploration just to these A2 and A3 actions in state S3, ignoring sort of the actions or the samples you might have to allocate to S2 otherwise. And you can get sort of a reduced sample complexity in this case. You don't need to pay this 1 over epsilon squared. You can pay sort of a lower scaling in epsilon. Okay, so this is kind of the intuition for this example and why you're able to sort of get an improvement statistically and sort of offline, using offline data.
I have a quick question again about this example. So like in the purely online case, I see why you would need like this 1 over epsilon squared number of samples from S3.
Mm-hmm.
But like now, if you've run this offline data set, which has some coverage of like S2 and S1, but not S3, right? Then you were saying you could like dedicate more of your online sampling to S3, but how does it become like this like 1 over epsilon to the 8 over 5? Like what I understand is basically without the offline data set, you kind of like have to evenly distribute your sampling. But now like the offline data set covers S2 well.
Yeah.
And so like now you can just like dedicate exploration to S3, but like it's quite weird to me that it becomes in this like way.
Yeah, no, so the reason it's 1 over epsilon to the 8/5, like intuitively you actually might think there's like maybe like O of 1 samples to solve S3. The reason it's 1 over epsilon to the 8/5 is I didn't like explicitly put this in the theorem, but this lower order term. So we have sort of this main leading order term. We have a lower order term, and this lower order term scales with 1 over epsilon to the 8/5. The reason I'll explain in a bit, like sort of where this comes from. There's not great intuition for why it's to the 8/5. It's less than epsilon squared, so it's sort of like lower order in that sense. But that's actually why if you just looked at the leading order term here, the TO20, if I just written the complexity in terms of that, you wouldn't have this 1 over epsilon to the 8/5. This 1 over epsilon to the 8/5 is coming from this like lower order term we get in our complexity, which we don't know how to remove annoyingly. That's why it's this like weird thing. Like it's not like a normal complexity. It is less than 1 over epsilon squared, so you are actually getting an improvement. But you might hope it's O of 1, and like if you just looked at the leading order terms, it would be. But given this sort of this kind of annoyance with this lower order term, we can't. We at least our theorem doesn't give us that.
Yeah, a related question. So if we disregard the algorithm just for a second, and then we just think about, okay, what would be a reasonable algorithm for this case? Have you thought about this? And what sample complexity you would expect for that algorithm when it's using both offline and online data?
Yeah, I mean, yeah, I think the right complexity actually for this example in particular, I think you should be able to do it in like order 1 online samples because you can solve this state actually quite quickly. And so the really heavy lifting that has to happen in this example is in state S2, which is solved by the offline data. So I think you should be able to, and indeed, you could certainly construct an algorithm that would do the right thing here. The question is like, is it going to generally get the right thing for all linear?
I have a clarifying question. So my understanding was that the probability of transitioning from S1 to S3 is square root epsilon.
Yeah.
So if that is the case, then there is a little like if I can only start online data collection from S1, then I have to wait quite a bit.
Yeah. So actually, I didn't state this here, but the actual construction is so you have 3 actions. So it's constructed so that action A1 is optimal, and that will transition to S3 with probably square root epsilon. But one of action A2 and action A3 will transition to either S2 or S3 with probability 1.
I see.
So you can direct your exploration to any state you want to go. Essentially,
Right.
you have
it's
to
not just like rarely seeing S3. I see.
Yeah.
Okay. That it becomes so on. Yeah.
And so the example highlights that like basically the offline data can cover places that you couldn't visit online well, like sometimes.
Well, like in this case, you could visit state S2 online. Like it would be easy to collect data in state S2 online. It's just that like you don't have to anymore because the offline data gives you that coverage.
Right.
Some other example might be like what you're saying, Vlad, but not this one.
Yeah.
Uh-huh.
Yeah. Okay, maybe I can move. I'm actually like running low on time, so maybe I should like keep.
Yeah, go ahead.
Okay. So I want to make one comment here on sort of this question of how does our complexity compare with C star. So we require this kind of slightly stronger coverage condition than C star, and that C star essentially would only say you need your data, you need phi pi star to be small. In this sort of data coverage. What we're saying is we actually want every policy to be small, the sup pi, but how small it needs to be, it kind of is like weighted by how suboptimal this policy is. And so this is kind of like stronger than just a C star coverage conditions because we really need coverage on all policies. And so you kind of might wonder, like, is this like necessary? And I guess sort of the answer is it kind of is, or actually it actually is, if depending on sort of what kind of a result you want to get from your algorithm. And so let's just think about like a really simple example of a multi-arm bandit. And so what I'm showing here, these arrows are the reward means. And let's say we have some amount of offline samples, and so on the best arm, we have a lot of samples, and on all the other arms, we just have like 1 sample. Now, if we construct our confidence intervals on these arms, what we'll see is that the confidence interval on the best arm is actually quite small because we have all this data. The confidence intervals on all the other arms are like relatively large. Now, let's think about like running standard offline algorithms. What do they usually do? They usually apply pessimism, which will choose sort of the largest LCB, lower confidence bound. In that case, it's going to choose the first arm. And so what we'll get in this case is that pessimism, offline RL, will identify the best arm. But it actually can't, it's sort of like doing something weaker than we often think about when we sort of think about like online RL or online bandits, because it doesn't actually have enough information to like verify this is the best arm. Because the confidence intervals of the first arm and on all the other arms are actually still overlapping. And to verify that arm 1 is the best arm, we actually need additional data from all the other arms to make the confidence intervals non-overlapping. And so if we want to just apply pessimism, we can identify the best arm, and we can do it without collecting additional samples. But if we want to actually verify it's the best arm, we require additional samples. And so this is kind of like why we're seeing a different, stronger coverage condition necessary here, which is that pessimism, or these offline RL algorithms typically give like sort of unverifiable complexities, which it's essentially like a luckiness result, which is like if you get lucky and your data happens to cover the optimal policy, like this will return a good policy, but you can't actually verify necessarily that it has this coverage. Whereas often in online RL, these like PAC guarantees, we actually want to sort of have an algorithm that returns an epsilon optimal policy with probability of 1 minus delta, which is more of a sort of a verifiable guarantee, where like we sort of want an algorithm that we can ensure is always like succeeding. And so you can show sort of formally that to do that, you actually need this like stronger coverage condition, which is why we don't get this sort of like C star coverage condition precisely. Okay, so that's kind of just an aside on in terms of like why this coverage is seems to be necessary. I think I want to talk a little bit about the sort of how we actually collect the data, but I don't should I spend a few minutes on this or should I like wrap up here?
I think you can spend like 5 minutes on this.
Okay.
If you can do it in 5 minutes.
I'll try to do it in 5 minutes.
Okay.
Okay, so there's a question here now. How do we, at the critical step in our algorithm was collecting online data, lambda, such that it augments the offline data, the coverage of the offline data, in some like nice way, ensuring that sort of for all the relevant directions, we sort of get this coverage is less than epsilon L squared. So the question of how do you actually collect your online data to do this? And it turns out, so this actually method was actually developed in this previous paper I've mentioned a couple times, but we extended it to the offline data setting. So why is this hard? Well, we don't know how to get to some direction phi. Like we don't know how the MDP works in general. And so we want to augment our offline data with online coverage, but we don't know how to collect online data that will give us that coverage. And so what we're gonna essentially do, or the gist of it is the following, which is we apply, so we sort of can think about this question of finding this good data coverage as sort of an experiment design problem, meaning that we want to find some exploration policy, call it pi exp, such that sort of in direction phi for all relevant phi, in this case phi for our active set, this confidence interval is small for our offline data combined with the online coverage induced by pi exp. So we can sort of like reduce this data collection problem to something like this. Find an exploration policy pi exp such that for all relevant directions, the offline data, in this case we denote by lambda naught, combined with the online data gives us good coverage. Okay, so how do we actually solve this? So to do this, we take inspiration from the Frank-Wolf algorithm. Now the Frank-Wolf algorithm is sort of a kind of a standard approach to optimization in general. And it sort of runs just like two simple steps. The first step, it computes the gradient of the function f it's trying to optimize. And it finds some point in the constraint set, x, that has sort of minimal inner product with the gradient. And then it updates the current iterate as some weighted average of that. And you can show like under standard conditions or under like convexity, smoothness, whatnot, that this works. After n steps, you sort of converge into 1 over n, right? So if we sort of like knew exactly if we go back to the problem we care about, a standard way to solve problems like this is to apply something like the Frank-Wolf algorithm. The challenge in our case is that we don't actually, what we want to minimize over is this exploration policy pi exp. And we don't know what coverage pi exp will induce. That's denoted by this lambda pi exp. So if we were to write down the Frank-Wolf update, we get something like this, where we're optimizing over policies pi that sort of have large or small inner product with the current gradient on our loss in terms of their coverage. But we don't actually know what this lambda pi is, so we can't actually solve this optimization problem. So what we observe, though, which is kind of the key observation, is that you can sort of just rewrite this optimization problem into this form, min over pi, sort of the expectation of phi of sh, ah, so the expected essentially feature vectors, policy pi encounters, inner product with some matrix chi, which is just this gradient matrix. And the point here is that this is actually just a policy optimization problem. And so we can apply sort of standard regret minimization algorithms to solve this policy optimization problem. And so this is essentially the idea for our algorithm, which is that we reduce solving this experiment design, collecting sort of this good online data to sort of a sequence of policy optimization problems, each of which is one step of the Frank-Wolf algorithm. And then we can run some regret minimization algorithm to solve each step of this policy optimization problem. And the key point here, you might be like, oh, why does this, like this seems like kind of chicken and egg, like, you know, I'm solving a policy optimization problem to collect good data, which I'm then going to use to find a good policy in the end. The reason this works is that you only need actually a very coarse solution to this policy optimization problem to learn like a good enough exploration policy. So you can sort of show you can do this efficiently, and then this actually allows you to sort of get basically the optimal rate for exploring. Like basically you can show that you collect data satisfying your condition, the desired condition at roughly the optimal rate. That is up to lower order terms, and that's where that 1 over epsilon to the a fifth comes from, because there is some cost you pay to running this. But in terms of leading order dependence, you can sort of argue that you explore at the optimal rate. Okay, that was really quick. I'm happy to chat more about this. People have additional questions on how that all works, but I think I'll just leave it here for the moment. Thanks.
Yeah, great. Thanks.
Thank you.
Questions? Let's see whether people do have questions. This last part was indeed quite dense. I guess
Yeah.
you put a full paper in 5 minutes.
Yeah.
Yeah. So there was something going on with this Frank-Wolf that the Frank-Wolf algorithm, there's this y's and x's, they live in the same space in a way.
Mm-hmm.
In your version, we are going between policy space, I guess, and then covariate space, and like, okay, that was like quite a leap for me.
Yeah. So the way I actually wrote it in the paper, which I didn't write it here, maybe it would have made more sense if I had, is you can actually really think about all of these as covariate space. So like when you optimize over, like the Frank-Wolf update is this equation here. When I optimize over policies, I can really think about what I'm doing is actually just optimizing over covariance matrices. And the set I'm optimizing over is a set of all possible covariance matrices that like any policy could induce. But you can equivalently write this as an optimization over policies or covariance matrices.
Yeah.
And so what I actually like proved this, I wrote it as covariance matrices because of what you're saying. Like otherwise you're kind of jumping between spaces, which is a bit weird. But sort of conceptually, it's doing the same thing.
Sometimes when you're jumping between these spaces, there is a problem with non-uniqueness and stuff like that. So that doesn't happen here.
That was not an issue here, no.
Yeah.
Because it's basically you can argue that the set of all covariance matrices is just some like continuous convex set actually, and so you're essentially optimizing over like distributions over this like continuous convex set, and it was like not, yeah, it wasn't.
And the fact that you can keep the covariance matrices themselves, actually, I think that's yeah.
Yeah. So what we actually end up doing is like
avoid this problem.
As I say.
Go ahead. No, go ahead. You were saying.
I was gonna say like yeah, when you actually run this, what this returns is actually not an exploration policy. We just set it up so it just simply returns a covariance matrix because all you want in the end is like your data. So it essentially just like optimizes in a way that like you get to the end and instead of returning some set of exploration policies, you would just return the covariance they collected. Though you can actually you can actually adapt it so it returns an exploration policy, which you can then rerun to collect your data. So either way can be used. But
you already collected the data by running this. Algorithm, so you just take the covariance matrix for that, right?
Right.
Yeah.
So yeah, this is essentially like, I mean, what I'm doing here is just like more or less like a G-optimal experiment design. The key thing though is that usually when you think about G-optimal design, at least for things like linear bandits and whatnot, we sort of assume we know all the X directions that we can optimize over. Here we don't know what those directions are because we're optimizing over this like unknown set of possible covariance matrices. And so the way we get around that is, yeah, we sort of run this like regret minimization algorithm to sort of like find the best directions.
Right. So this set of covariance matrices, do we know it's convex?
Well, so the way I formulated it, yes, because like you can take like the way basically how I define the set is like over all possible mixtures of policies.
Uh-huh.
So you fix
Uh-huh.
whatever space of policies you want.
Yeah.
Consider the set of covariance matrices induced by that, and then just take all the mixtures of those policies, and you get like a convex X. It's just a combination of.
So then but when you're running the policy optimization, I guess you only care about sort of the corners, so you don't have to worry about the mixture policies then.
Yeah. So you only like you can get away with just.
Yeah.
So I don't remember where's. Oh yeah, here is it. So you can get away with just like solving a single policy optimization,
Yeah.
and then if
Right.
you were to return a thing at the end, you would return like the mixture of all
Right.
the policies.
Yeah.
Yeah.
Okay. Right. So this choice of working with linear MDPs, I like linear MDPs because they seem to be a nice generalization of tabular MDPs. At the same time, they seem to behave slightly differently than tabular MDPs, right? Like reward-free optimization or reward-free learning is kind of free in linear MDPs, where this is not free for tabular MDPs. So I was wondering whether, so these algorithm as well, it's sort of just doing this reward-free optimization under the hood, right?
Well, I mean, like
Sure.
not quite. So like, I guess what it is doing is it gradually is like refining the set of policies.
Yeah.
So basically maintains a set pi L, which it gradually will shrink into only maintain good
But the
policies. So
reward
very much
comes
actually
in when
depends
it's
on the
doing the
reward.
elimination. Yeah.
Yeah.
Right. Yeah. Okay. Yeah, I remember. I noted it. It's just like the step that is running the online experiment design ignores the rewards.
Yeah. So that ignores the reward, but it's kind of baked in which directions it's trying to like explore. There's only trying to explore the directions in the active set. And so it kind of is like focusing its explorations just on like the, direction spanned by high reward policies.
Right.
Yeah.
Cool.
And we have actually, this paper, this algorithm is based on this pedal paper. We sort of get a similar result to this, but just with no offline data. And sort of we have some examples in that paper showing like various things, like this sort of more like instance dependent guarantee is able to improve on is able to get tighter results than like worst case guarantees and stuff like that. So this is like buying you something even just without offline data actually to do something like this.
Maybe I'll stop recording here.
Okay.